Welcome back to the Inside Java podcast, a podcast about everything Java brought to you from the folks at Oracle who make Java. My name is Ana Maria Mihalceanu, and I'll be your host for this episode. Today's episode will be a conversation I had with Stuart Marks, the owner of Job 431, about sequence collections. Stuart and I briefly discussed about the characteristics of collections framework and missing abstractions, the essence of sequence collection interfaces, and what many common problems this new collection type solves. So enjoy the show. Stuart, welcome. Probably many of us actually know you as Dr. Deprecator. It's a beloved name in the Java community. So welcome back to the podcast. You're pretty familiar with this kind of show so far.
Yeah, hi. It's good to be here again.
Well, I'm very excited to interview you today. And it's on an important topic for many of us developers because we all use collections, and that's today's topic. Can you make a mini recap on collection history, when they were introduced into the JDK, and what major changes have we got since then?
Yeah, sure. Okay, so collections are, they're pretty old API. So they were introduced in JDK 1.2 all the way back in 1998 or so. And so that's where we got our familiar list, set, map, and collection interfaces. And there was a fairly bare bones set of implementations. And then in Java 5, the concurrent collections were introduced along the way. Actually, sorry, rewind a bit. 1.4, linked hash set, linked hash map, priority queue were added. And then moving forward in Java 9, the unmodifiable collections, that is list.of, set.of, map.of, were added. And those, those were enhancements to the collections framework proper. Java 8 had streams, which are sort of an adjoint to collections, but didn't affect collections all that much. So one of the things, though, in the collections history is that the collections interface hierarchy represents a family of abstractions. And so a list is an interface that represents a collection with certain characteristics. So is a set, so is a map. And then there's some sub-interfaces like navigable map and navigable set that have some variations on that. But one of the things that's missing from that hierarchy of abstractions is the notion of order, or what we call encounter order. And it's rather peculiar because some collections have an encounter order and others do not. But that's not represented at all in the interface hierarchy. And so that's something that's been something that's been missing, and people have been asking for on and off during that entire history of the evolution.
Well, speaking about what we were missing, and this new type of collections that gets to be introduced by Job 431, what many common problems do the sequence collections solve?
Yeah. Okay. So one of the things is, like, if you have a set, for instance, the set does not have a defined encounter order, and so a common collection implementation of a set is hash set. And so since it doesn't have an order, you can't say get me the first element or get me the last element or anything like that. On the other hand, there was a subclass of hash set called linked hash set that does have a defined encounter order. And it has actually not many more APIs. I don't know. I'm not even sure it has any APIs added to the basic set. Now, it does have a defined notion of an encounter order, but it doesn't have any methods that let you do anything with it. So, for instance, suppose you wanted to add something to a linked hash set. Well, it goes at the end. So new things get added to the end. But suppose you wanted to add something to the front of a linked hash set. Well, you basically can't, unless, of course, you just want to rewrite the entire contents of the collection, which is kind of unreasonable. Also, if you start iterating a linked hash set, it starts at the first element, and the iteration proceeds to the last element. So it's not too difficult to get the first element it's not too difficult to get the first element of a linked hash set. It's a little tedious. You create an iterator and call next on it. But you can get the first element that way. But now get the last element of a linked hash set. Well, you basically can't without iterating through the entire collection. So that's one of the things. Even though linked hash set has a notion of ordering, and it does have a first element and a last element, you can't actually operate on them. Now, there are some other problems as well. So, for instance, a list, everybody's familiar with a list. List elements are definitely ordered, and you can get the first element, last element, but they're numbered. So the first element is 0. So you can say list.get0 or list.remove0. Now, how do you get the last element? Well, okay, so you can get a list size by calling the size method, but the elements are numbered from 0 to size minus 1. So if you want to get the last element of a list, you have to say list.get list.size minus 1. It's not a huge problem, but it's kind of tedious. And then, of course, if you forget the minus 1, then you get an index out of bounds exception. And
we've all done that.
Yeah, exactly.
I'm not ashamed to admit it. Happens to every developer.
Absolutely, right. This is something that everybody's run into, and it's just something that people use lists all the time, and you have to remember. Oh, yes, in this case, I have to add the minus 1, and sometimes you forget, and it blows up.
Well, that's cool to hear. Well, speaking about sequence collections, what new methods do these bring to developers?
Right. Okay. So I started talking about the interface hierarchy, and so the sequence collections JEP adds 3 interfaces to that hierarchy: sequenced collection, sequenced set, and sequenced map. So let's set aside sequenced map for the moment. But sequenced collection is it's the core of the new additions, and that gets inserted between various ordered collections. Like you have to look at the diagram, and there's one linked from the JEP, and I'm sure the show notes will have a link to the JEP. But yes. It's inserted between collection and, for instance, list. And so what it does is everything that inherits from it gets a family of new methods. And so one thing we were talking about just a moment ago was operations at the ends. And so, for instance, I was talking about linked hash set and getting elements at either end. So those are new methods that are added to sequenced collection, which are get first and get last. And you can also remove the first and last elements. There's remove first and remove last. And there's also the ability to add elements at either end, add first and add last. And so those are inherited by list. They're also inherited by linked hash set and other interfaces, including deck and what's the other one? Oh, navigable set. Also inherit those methods. Actually, those methods I just listed were already on the deck interface. And so effectively, those methods were promoted from deck up to sequence collection, where they can be inherited from, inherited by other parts of the collection interface. So there's kind of the general scope is there are six new methods for access at either end. There's add, get, and remove, and first and last. So that gives us six of the operations at the ends. In addition, there's another method called reversed. And what that does is it provides a reverse ordered view of this thing. And so if you look at the way mini collection operations work, like iterator or stream or toArray, they come out in some order. And if the collection has a defined encounter order, then of course the elements are iterated, or they're copied into the array, or they're streamed, or whatever, in that collection's proper encounter order. And sometimes what you want to do is operate on the elements of a collection in reverse. And that's another, actually, I'll take another quick aside here. That's another problem that comes up from time to time in the collections framework prior to the addition of sequence collection, which is that for some things it is really difficult to iterate in reverse order. And the other thing is, even if you can iterate in reverse order, it's different for every collection. So for instance, with a list, you can index from size -1 down to 0, or you can get a list iterator and step through it by saying has previous and previous. The deck interface has a descending iterator, which is a little bit nicer. But that's kind of a pain to use because you have to use an iterator. And iterators are kind of old-fashioned at this point, now that we have the for each loop and now that we have streams. So if you wanted to get a stream in reverse order from a deck, it's actually kind of hard. You have to get the descending iterator and then call stream support some splitterator from iterator. I forget exactly. I mean, there's a little idiom to do that, but you have to call a few methods in order to get a reverse ordered stream. And then let's see, navigable set. Let's not forget about that. That actually has something very nice on it. It actually already has a reverse ordered view. It has a different method name, descending set, but navigable set already has a reverse ordered view built into it. And so that's nice. But then there's our old friend linked hash set. It's basically impossible to iterate that in reverse without copying all the elements into some other collection, in which case you might as well not bother.
Speaking about reversed method, I looked in through the JEP, and one thing that drew my attention is like initially, now sequence collection becomes the super interface, both for list and for deck. However, I've seen that a reversed method not always returns a sequence collection of a certain type. So can you talk a little bit more about why is that happening and how does that happen?
Yeah, sure. Okay, so there's a feature in the Java programming language called covariant overrides, and so it's a little bit obscure, but it comes in handy from time to time. In particular, in this case. And so the general idea of covariant overrides is, suppose you have some. I guess I'll have to speak a little abstractly here. Suppose you have some method M in some class, and it returns a return type R. Okay. Now consider a subclass, and you can create a subclass, and you can override a method in a subclass. And so the subclass has a method M. So that the overriding method can also return R, or it can also return a subtype of R. So it's called covariant because we're saying in a subclass, you can return a subtype of the parent's return type. So there's sort of, it's a little abstract, but it's covariant because the subclassing goes in the same direction. So a subclass can return a subtype. That's basically what it is. And then things sometimes go in the opposite direction. That's kind of a different story. But anyway, so that's the feature, which is if you're overriding a method from a superclass, if you're in a subclass, you can override a method from that you inherit, and you can return a subtype. So how does that get applied to sequenced collections? So suppose you have a variable of type sequence collection and you want a reverse ordered view on it. You can call a reversed, and that returns a sequenced collection. And that's kind of nice because you still have all the collections methods, but you also have add first, remove first, add last, remove last, and so forth. But since this is a reverse ordered view, all of those operations at the ends are now inverted in the sense. So add first on the reverse ordered view actually ends up adding the last element to the original collection. All right, so that's kind of nice because you can, if you get the reverse ordered view of something, you get the same type back, and you can do all the same operations on it. But now we have list as a sub-interface of sequenced collection. And so what happens when you call list.reversed? Well, list has a bunch of other stuff on it, like, getting by index or removing by index or saying index of or something like that. So if list.reversed were to return a sequenced collection, you would lose all of those extra list methods. And that, it would still be useful, but it wouldn't be as useful as it could be. So what we've done here is we've said, okay, in the definition of the reversed method of list, we define a covariant override. So list.reversed returns a list because list is a subtype of sequenced collection. So anyway, if you have a list and you call reversed on it, you get back a list, and you have all the same set of operations. You have the indexed get, you have indexed add, indexed remove. It's just that everything is, operates on the original underlying list in the reverse order. And I don't think I made this clear, but I'll now that I recall, the whole the whole point of the reverse method is that it doesn't reverse the collection in place. It does not mutate the collection, and it does not provide a new copy of the collection. It provides a reverse ordered view. So operations on this view end up operating on the original collection with their direction inverted.
Well, that's great to know for our audience. And well, since we're talking about how reversed is working, and how does these new super interfaces affect different existing collections? I'm thinking about the collections, the edge case of the collections that position elements by relative comparison. I mean, sorted set, tree set. In that case, you cannot add at either end. So how do sequence collections work in those cases?
Yeah, so that's one of the unfortunate asymmetries in the design. And the first thing to understand is that there are some collections among the collections that have an encounter order. You have to ask the question, where does the order come from? So with a list, the elements are positioned explicitly. And so if you add something at the end of a list, it just goes at the end of the list. Or you can add something at a particular position at index K, for instance, and the element just goes there. So that's explicitly positioned because it's manifest in the API that you want to put this element there. Now, there are other collections, in particular navigable set, where it also has an encounter order, but you do not have the opportunity to position elements explicitly, because the way a navigable set works is you either have to put elements into it that are comparable, or you provide a comparator. And so it's this comparison method that determines the ordering of the elements in a navigable set. So if you take a bunch of elements and throw them into a navigable set, they get sorted according to that comparison method. So it doesn't make sense to say, here, put a bunch of elements in and have the navigable set sort them for you. And then, by the way, here's another element. Make sure it's at the front. Well, that clashes with what we just said, which is, you can't necessarily put this element at the front because it might belong in a different place in the sorting order. So how is that going to work then if we have sequenced collection that has add, get, and remove at the first and last positions? And how do you reconcile that with navigable set? Well, get first and last work and remove first and last work, but add first and last do not. It simply doesn't make sense to say, take this element and add it as the last element of a sorted set. Or a navigable set. Because, it might not belong there. So the unfortunate result is that for add first and add last on navigable set, we have to throw unsupported operation exception. So in that sense, navigable set doesn't fully implement the sequenced collection or sequenced set interface. And so, yeah, so that's an asymmetry in the API, to be sure. However, what are the alternatives to doing that? Well, I don't think we have enough time to go through all the different alternatives, but I did investigate several of them, and quite frankly, they're worse. So I think this is one of the ways that you have to deal with things in API design. There are always trade-offs. There are always going to be asymmetries somewhere. And so you choose the design that makes the most sense and is the simplest and has the fewest asymmetries.
It's very, very good to know for me as a developer and for our audience as well. And I think it's great that we see so many improvements on the well-known interfaces of the collection framework. But myself, as many others, have used quite a lot the collections utility to operate on collections. So how about that one? Are there any additions to the collections utility?
Yes. So the collections class has a bunch of utility methods for just doing a variety of operations on collections in general. Probably, I mean, there are a few methods that are added there in support of the sequenced collections interfaces. Probably the most important ones are the ability to take a sequenced collection and wrap it in an unmodifiable wrapper and return a sequenced collection. So, for instance, this is pretty useful. So, if you suppose you have an array list that's you can add and remove elements from it, but you want to hand that reference to somebody else, you can wrap it in an unmodifiable wrapper by saying collections.unmodifiableList. You hand out that reference, and you can be assured that they cannot modify your array list. So that's been there all along, and list is not affected by this. But suppose you have a linked hash set, and you can add and remove elements from that as well. But suppose you want to hand out a reference to that linked hash set to somebody, and you don't want them to be able to modify it. You could wrap that in collections.unmodifiableSet, and so they would get a set which loses all of the nice sequenced methods, like getting the first and last elements or getting a reverse ordered view. So there's a new method, unmodifiable sequenced set, that is that same wrapper. It's just that its return type is sequenced set. So you can take a linked hash set, wrap it in the unmodifiable sequenced set wrapper, and then hand that out to somebody, and they can use more flexible operations on it. So they can iterate that in forward and reverse order and get the first and last elements and stuff, but they cannot modify it. There's also another one which is related to maps. This is a bit obscure, but it turns out to be incredibly useful. Given any map, there's already a method called newSetFromMap that converts the map into a set, and so that's, for instance, that's how you can get there's a thing called concurrent hash map in the Java util concurrent package, but there's no concurrent hash set. So, what do you do about that? Well, you can just take a concurrent hash map and convert it into a set using collections.newSetFromMap, and that works great. Well, suppose you have a sequenced map, and how do you convert that? You can wrap that in newSetFromMap, and you get a set. But you might need a sequenced set. So there's another little utility in there which does something very similar, which is new sequenced set for map. So if you have a sequenced map, you can put that wrapper around it, and you can get a sequenced set out of it.
While looking through the JEP, there's something else that caught my attention while looking at the sequence map API. As it ends with a map, my expectation was to use a naming strategy similar to that one. To my surprise, there is no get first entry, but first entry. And instead of remove last entry, there's poll last entry. Can you please tell me a bit about the sequence map nomenclature and maybe share some examples that encourage that?
Yeah, sure. So that's sort of the obvious thing. If you have sequenced collection, it has this nice system of add, get, and remove first and last. Okay, great. So with sequence map, you might expect there to be add, get, and remove first and last as well. Now, functionally, we have all of those we have those mechanisms. but they just have different names. So why is that? Well, if you look at navigable map, there isn't anything that's called get first entry or anything like that. On navigable map, there is already a method, or there's a pair of methods, first entry and last entry. And those are kind of the getters. They just have different names. So I think it just to avoid proliferation of new redundant methods, I reuse the existing APIs from navigable map. So instead of get first entry, there's already one called first entry. And so that got promoted up to sequenced map. Similarly, there's no remove first entry in navigable map. It's called pull first entry. Now, why is it called pull? Well, this kind of comes out of the concurrent data structures where if you're a thread, you might pull a queue to see if it has an element. And if there is an element, it removes it and gives it to you. And if there isn't, it returns null. You can actually use a navigable map this way. You can you can throw a bunch of things in, and you can pull them out in sorted order by using the pull method. It's sort of the same thing, but again, their methods pull first entry and pull last entry already on navigable map, and so those effectively have the same semantics as remove, although it is somewhat different. If the actually, this applies to first entry and last entry as well. If the navigable map is empty, those return null to indicate that the map is empty. They do not throw exceptions, which is kind of a difference from sequenced collections. But again, this is actually the semantics of those existing methods on navigable map. They return null instead of throwing an exception if the map is empty. So on the one hand, sequenced map is perhaps disturbingly inconsistent with sequence collection because these methods have different names and they have different behavior. On the other hand, we have these methods already on navigable map, and so it makes sense to reuse them and promote them up to sequenced map, which is a new super interface of navigable map. And then finally, to round out the set, you don't add things to a map, you put things to a map. And so instead of putting an entry, we just put a key and a value. And so there are new put first and put last methods added to sequence map.
A curiosity of mine is about the performance impact of using sequence collection. Is there anything that you can tell about that?
Yeah, most things, the operations at the ends really do not impact anything. I mean, so for instance, if you have a list already, and get first should be the same performance as get zero, and same with add and remove and so forth. I think the performance impact that you probably need to be aware of is operating on the reverse ordered views. And so the question there is how much effort we're going to put into optimizing reverse ordered views. Because the fact is there is a certain amount of overhead. You're operating on a view, and so that has to delegate operations to the underlying collection. Certain things still need some work, and it's unclear how much performance we can get out of the system. For instance, suppose you have an array list and you run a parallel stream on it. That's highly optimized because what it can do is it can take the array, it can split the array into left and right halves and do so recursively and operate on those elements and subsegments in parallel. And that all works great. Now consider doing the same thing on a reverse ordered view of something like an array list. You could do the splitting, but everything is in reverse order. And I think right now, in the in the implementation as it stands right now, it's probably fairly slow. But even so I have plans to optimize that. But even if I optimize it, it's still essentially iterating the elements in reverse order. And computers don't necessarily like that. it's always faster to iterate forward because our computers have things like prefetch that say, oh, you just crossed into a new cache line. I'm going to load the entire cache line, and I'm going to prefetch subsequent cache lines in anticipation of you continuing to iterate forward. And I do not think they work quite as well going in the reverse direction. So there are probably going to be some inherent performance implications of operating on reverse ordered views of some of these collections.
Another curiosity of mine, I think we're like at the curiosity time of the questions. But I've also seen this with other folks in the public space when the sequence collections were promoted and showed to the public. Is that, for a long time, Java promoted code reusability. We practically grew up with that as developers. And I know there's a justification written in the JEP, but many observed that sequence collections and Deck look awfully similar. So a question that came up to many people's mind, and including myself, was like, why not repurpose Deck?
Yeah, so that's interesting, and that was in fact one of my earlier alternatives in considering this design, because Deck has almost, well, actually, it has almost everything that you need on it, right? So, as I noted earlier, it has add, get, and remove first and last, and it also has peek, and I think it has peek, pull, and I forget. It has a bunch of other methods. But the other thing is a deck is a queue. So one of the goals of sequence collections is to expand the applicability of this notion of having an order and having reversibility onto other existing interfaces, such as list and navigable set, as well as existing implementations like linked hash set. So we could try to do some surgery and say, okay, so let's reuse the deck interface, but instead of adding a new interface above deck and list, then rearrange list so that it also implements deck, and rearrange linked hash set so that it also implements deck, and same with navigable set. And maybe that could work. I didn't get that far with it. But if you look at that, once I started to dig into it, it became more and more distasteful. Because one of the problems is that a deck is a queue, and now we're saying that every list is also a queue, and every set is also a linked hash set is also a queue, and it's like, that doesn't necessarily make sense. And one of the things is that Deck also inherits a bunch of the single-ended methods from queue. So not only is there, add, get, and remove, and let's see, what was it? Oh, that's right. Like peek, pull, and take are the queue verbs. So it could do those at either end, and it could also, there's peek first and peek last. But queue also has a plain peek, which implicitly goes at, operates on the head of the queue. So all of those exist in Deck. And if list were to inherit from Deck, then not only would list get the nice, add first and add last that we wanted, but it would get this whole range of extra queue methods. And if you start working with things like that, then it just started not to make sense. So in a sense, the design does do reuse, because it reuses from Deck. It reuses add, get, and remove first and last. It's just that it moves them to a higher interface from which they can be inherited in a more graceful way, as opposed to trying to reuse the entire block of Deck. And in fact, it's a fairly cluttered interface that would get inherited everywhere.
I think that makes much more sense now. I think we should wrap up. I know you're a very busy person, and I truly appreciate that you took the time to come here and talk to us about the sequence collections. So as a last question, I'm curious to know about your opinion about where Java, the language, and the platform are going, the connection to sequence collection evolution.
Yeah. Okay. So there's a lot of activity going on in the JDK. There are some large projects that have been running for a long time, and the one in particular that comes to mind is Project Amber, which is a set of enhancements to the Java programming language to make everyday programming easier. And there are a bunch of different features in Amber, but I think one of the more promising ones is pattern matching. There have been a series of JEPs enhancing instance of and switch and records, and they all play together very nicely. So what does that have to do with collections? Okay, so one of the things that pattern matching lets you do is it's an interesting construct that arises from functional programming languages like ML, which is you can look at data, and if what you're asking for matches a pattern, then you can automatically perform extraction of constituents of that data and bind the results into variables. And it turns out we do a lot of this with collections. Like, for instance, suppose you have a list. You might want to process the first element and then take the rest of the elements and do something else with them. In functional programming languages, that's actually a fairly common idiom, which is to have kind of a first and rest pattern. Now, we don't have that yet in Amber. So Amber right now in preview has pattern matching features related to records. And the reason that that team started with records is that they're easier. And so the interesting thing about a record is that a record's structure is exposed to the programming language. So if you define a record, you say, if I have a record int A, int B, int C, brace, brace, right? I mean, that's very nice syntax, but you've declared several components there and they have names and types, and that's known to the programming language. And so that makes it amenable to pattern matching directly on the values of those components. One of the steps that the Amber team is thinking about where to go next is how to apply pattern matching to classes in general. And so I think there are a large set of use cases that we need to explore with collections to expose patterns arising from various collections. And so I gave an example a moment ago. If you have a list, sure, a list has a first element, or you might want to pattern match the last element of a list, or you might want to pattern match the first element and the rest of the elements. If you have a map, you might want to do a pattern matching over testing particular contents of a map. If a map has a mapping for this key, then process its value as as follows. So it turns out, if you look at the way that a lot of code deals with collections, it does this sort of thing all the time. If a list is not empty, then get the first element and maybe remove it and process the rest, or iterate over it. Or if this map has a mapping for this value, then do something with it. And that's a pattern matching and extraction. And so this is all pretty vague at this point because we don't have a syntax for that. We don't have a very clear idea of how general classes can expose the right parts of themselves to the language's pattern matching mechanism. But I think that's a very promising area of investigation. I'm already talking to the LangTools team about how that might look. And I think they're looking in the same direction. I think they want to figure out how pattern matching can be applied to general classes. But the fact is, we have a ready-made set of classes here that represent data, which is the collections. And so I think there's lots of useful things we can try to investigate in considering pattern matching over collections.
That's very inspiring. Well, thank you, Stuart. Thank you for your time today. and looking forward to hearing more about the future of Java.
Thanks for having me on the program.